Okay, Luhn's algorithm is applied to credit cards to calculate their checksums and their check digits. So here's a typical credit card number, and the idea is that we split the numbers up into the odd numbered positions, so first, the third, fifth, etc., and the even numbered positions. We can do it like this fairly simply if we write them on two different rows. That's probably the easiest way to do it. And don't forget the check digit is going to be always in the even position because it's 16 numbers. And then we do like last time, give each of these a weight. So the odd numbered positions are going to be weighted by 2. So we add these up. We've had 4, 0, 0, 1, 3, 5, 7, 9, add it up, and you end up with 29. And it's going to be multiplied by 2. That's the weight for the odd numbered positions, and the even numbered positions are going to get a weight of 1. So we add up 0, 0, 0, 2, 4, 6, 8, 9. That also ends up being 29. Now that's just a coincidence. 29 and 29 are the same. Now that doesn't always happen, but it's weight. Each of these, 2 times 29 is 58, and 29. Then we're going to add those, but there's also something else we're going to add, and that is a count of all the odd positioned digits which are bigger than 4, greater than 4. So 4 is not bigger than 4, neither 0, 0, 1, 3, but 5 is, 7 is, and 9 is. So we're going to add 3 into that sum. And if we add that up, we end up with 90. So the checksum is twice the sum of the odd positions numbers plus the sum of the even positioned numbers plus the number of digits greater than 4 in the odd position, and that's equal to, in this case, 90. And the important thing here is that this is congruent to 0 mod 10. In other words, 90 is a multiple of 10. In fact, that's exactly the condition we want for Luhn's algorithm. We want this checksum always to be congruent to 0 mod 10, or basically a multiple of mod 10. So this ends up being a valid credit card number. So let's now calculate what the check digit would be if we didn't know it. So here's an incomplete number. So 5, 6, 0, 5, 8, 3, 5, 1, 3, 0, 3, 3, 5, and an unknown check digit. So again, we split onto the odds and evens, odd positions and even positions, so it's easy to do it this way: 5, 6, 1, 0, 5, 3, 5. And the check digits down there. Again, remember we're weighting these by 2 and these by 1. So we add up 5, 1 all the way up to 5, and that turns out to be 30. And we're going to multiply by 2. All of these, 6, 0, 8, 5, all the way up to 3, ends up being 23, and we're adding the D. So that's 60, 23 plus D. And the last thing that we need to work out, how many of these odd position digits are greater than 4? So 1, 2, 3, So we're going to add 4 of them, and we add that up, and it ends up being 87 plus D. So we can write out, I'm just repeating this, 2 times the sum of the odd position numbers plus the even position numbers, the sum plus the number greater than 4 in the odd positions. That's equal to 87 plus D. And we want that to be congruent to 0 mod 10. What does D have to be? Well, the only thing that can be is 3, because we add 3 to 87, we get 90, which is a multiple of 10. So D equals 3. And that's our check digit. So quite straightforward. Now the point about Luhn's algorithm is that it detects a lot of things. So for a start, it detects 4 single-digit errors. So if you make a mistake in just 1 digit, it'll pick it up because the check digit won't be correct. It picks up all transposition errors. So if you reverse 2 digits, then the check digit won't correspond. Now, there's one wrinkle here. There's one exception. It can't detect the difference between 90 and 09. So if you have 0 and 9 together or next to each other and swap them around, the check digit actually doesn't change. We'll see that in the tick. And there are many other errors as well. So why doesn't it pick up 90 and 09? We'll think about where 90 might occur. So something, 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 90, something, something, something in the middle of it. Now let's just pretend this is in the even position and that's in the odd position. And then instead of this number, you accidentally write down 09. But think about the contribution that 09 makes to the checksum. So the weights are 2 times the odd position numbers and 1 times the even position numbers. So 90 contributes the 2 times the 0, because that's in the odd position, plus the 9, which is in the even position, which is 9. On the other hand, if you swap them around, transpose them, the 9 now contributes 2 times 9, because the odd position gets a weight of 2. 0 doesn't contribute anything or contribute 0, but because the 9 is now in the odd position, there's an extra 1 in that count of numbers greater than 4. And that's equal to 19. So 18 plus 1 is 19. And the trick here is that 9 and 19 are the same thing in the mod 10 system. So 0, 0, 9 and 90 are actually contributing exactly the same thing in to the checksum. Okay, I'll leave you with a little exercise for a minute. So here's a number, credit card number 567891112, and the question is this a valid credit card number? So if I get you to pause the recording for a bit and then work on it yourself, and then resume, or you can resume and we'll work through it together. So split them up into odd and even positions. 4, 4, 1, 7, 1, 2. Okay. Weight of 2, weight of 1. So add all these up and you get 31. We're going to multiply that by 2. Add up all those and you get 34. So we get 62, 34 plus in the odd positions, the ones that are greater than 4. So those 3. So we've got to add another 3 in there. We add those up and we get 99. So you can write the checksum is 2 times that 31 plus the 34 plus the count of big greater than 4 numbers there. That's equal to 99, and that's not a multiple of 10. So the credit card number is not valid.